In this video, I want to demonstrate drawing what are called Lewis dot structures. And we want to show molecular bonds between atoms. These are different kinds of bonds than ionic bonds. In an ionic bond, we had said that an atom, usually a metal such as sodium, would give its electron to a nonmetal such as chlorine. We said that for ionic bonds, chlorine wanted to have a full octet of 8 electrons, and it actually only has 7 in its neutral state. So if it was to interact with a sodium, then that 1 electron that sodium has could be given to chlorine so that chlorine would have a full outer shell of 8. That was an ionic bond. But what we're doing here is called molecular bonds. This is where the atoms will share electrons, and it's usually between 2 nonmetals. So hydrogen is considered a nonmetal even though it's on the left side of the periodic table. And when we draw a Lewis dot structure for hydrogen, we just want to draw its 1 valence electron that it has. And we can bring in another hydrogen because we want to see how hydrogen bonds to hydrogen. Now, neither one of them is going to be the metal in the situation. So it's not an ionic bond that they're going to form. It's going to be a molecular bond where we draw a line between their electrons, showing that they will share those electrons between them. And in this way, they can both be thought of as having a complete shell of 2 because they can both equally share each other's electrons. So how many electrons are shared when we have hydrogen bonded to hydrogen? It would be 1 pair. These hydrogen atoms share 1 pair of electrons, or 2 total electrons. Now let's see what it's like when we bond hydrogen with chlorine. In the Lewis dot structure for hydrogen, we'll just draw 1 valence electron. But when we draw chlorine, we want to draw 1, 2, 3, 4, 5, 6, 7 dots. And the 7 dots come from the fact that chlorine, it's in the second to last column of the periodic table. We see that chlorine is right here, and all the atoms in this column have 7 valence electrons, and that's why I drew 7 dots around chlorine. Next, we just want to connect 2 of the electrons to form a pair. And if we want to just draw a little bit simpler explanation of what's happening between hydrogen and chlorine, we could just draw a single line between them. And it's implied that that line means that they're sharing 2 electrons, or 1 pair. Now, for any nonmetallic atom that's bigger than hydrogen and helium, we want to make sure they follow what's called the octet rule. And that's that every element wants to have a complete shell of 8 when they're bonded. So we can count up the atoms that chlorine is in contact with. Okay, that's 1, 2, 3, 4, 5, 6, and then the single bond here accounts for 2 more. That makes 7 and 8. So chlorine is in contact with 8 electrons, and that's what it wants to fulfill the octet rule. when we have a Lewis structure drawn, we want chlorine to be in contact with 8 electrons so that it has that complete outer shell. Hydrogen's a special case. It doesn't have to fulfill the octet rule. It doesn't need to be in contact with 8 electrons. It just needs to be in contact with 2 electrons, and then it's satisfied when it forms a molecular bond. All right, let's try diatomic oxygen. So oxygen normally has 6 valence electrons, according to the periodic table. Oxygen is in this column here, and all the elements in that column will have 6 valence electrons. Now, since they're talking about a diatomic oxygen gas molecule, they are talking about having 2 oxygens bonded to each other. And so we can start by drawing one line between a pair of electrons that oxygen has, and that's a good start. However, we've not fulfilled the requirement of every atom being in contact with 8 electrons yet. We want to fulfill the octet rule for all applicable atoms involved here, and that's not fulfilled yet because this oxygen is in contact with 1, 2, 3, 4, 5, 6, 7 electrons. That's not enough. We need each of these oxygens to be in contact with 1 more electron than they're currently in contact with. So what we'll do is we'll rearrange things a little bit. We will form a second bond between the oxygens. If we want to draw it in a simpler way, we can do O and 2 lines between them. Now, how many electrons are they really sharing between them? This is 2 pairs. And that is 4 total electrons shared. Now, when valence electrons are not shared, they will often be drawn as being paired. And so we would just draw them close together. Electrons repel each other, so we want our pairs to be, far apart from each other. And if we just draw it a little nicer here, we could have this. Nice. Now let's try a diatomic nitrogen gas molecule. That's a nitrogen bonded to another nitrogen. If we go to the periodic table, we see that nitrogen is in this column here, where every element in that column would have 5 valence electrons. So let's go back to the Lewis dot structure and we'll draw 5 valence electrons around nitrogen here. Now nitrogen's only got 5 valence electrons around it, but it needs to be in contact with 8 total electrons in order to fulfill that octet rule. We can start by drawing one bond between the nitrogens, and that's good because now nitrogen is in contact with 1, 2, 3, 4, 5, 6 electrons, but it's still not enough. And since it's not enough, we'll want to introduce another bond, just like we did above. Now nitrogen is in contact with 1, 2, 3, 4, 5, 6, 7 electrons, which is almost what we need. But we need 8. So what's going to happen here is we're going to form a third bond. Now we may wish to draw this a little bit more symmetrical way here. Let's put the electrons that are bonded in the middle here. And then we can have the others on opposite sides, something like that. So nitrogen will have 3 bonds and 1 lone pair. If we count them up now, we'll have 1, 2, 3, 4, 5, 6, 7, 8. And that is what we need. You might also see it drawn like this. And that is a nitrogen gas molecule. How many electrons are shared between these atoms? 3 pairs, which is 6 total electrons in those bonds. Now let's try some more difficult molecules. Take carbon dioxide, for example. The di prefix means 2, and oxide means we're talking about the element oxygen. So we'll have a carbon bonded to 2 oxygens. And we want to start to think about what the shape of something like that might be. So would it be that the carbon bonds to an oxygen in the middle, and then that oxygen is bonded to another oxygen? That's one possibility. Or is it that carbon is actually the central atom here? Well, we'll find out once we draw the dots and try to figure out the puzzle of how they're bonded to fulfill the octet rule. Alright, so let's draw the dots. Oxygen has 6 valence electrons each. Carbon has 4, so we'll just put them on all different sides. How do I know carbon has 4? Because it is in this column. That is the column that has 4 valence electrons. Alright, so when it comes to the bonding here, the top arrangement may not work out well. Because see, carbon, it needs 4 electrons to bond to. And if I just bond it to this electron here in oxygen, that would give carbon 5 that it's in contact with. And that oxygen would need to be bonded to the other oxygen in order to make a molecule. And so the problem is that oxygen will have already fulfilled the octet rule here, and it can't bond to anything else. But that means the puzzle would not be complete because our carbon is in contact with 5 electrons. and our oxygen in the middle is in contact with 8 electrons, and this oxygen is only in contact with 7 electrons. So we have definitely not completed the octet rule in this formation. So we will not use that. Let's try the formation where carbon is in the middle and see if that works out better for us. I'll start by drawing all the valence electrons that all the elements have. And now let's try bonding carbon to oxygen on the right and carbon to oxygen on the left. So this is pretty good. We see that carbon is in contact now with 6 electrons, and oxygen is in contact now with 7. So the puzzle's not totally complete because they do need to bond to 8. They do need to be in contact with 8. So if we go ahead and make one more bond here, and one more bond here, then the puzzle will be complete. If we count them up, we see that carbon is in contact with 1, 2, 3, 4 on the right, and 1, 2, 3, 4 on the left. So that actually gives it a contact with 8 electrons. If we see how many oxygen is in contact with, it'll be 1, 2, 3, 4, 5, 6, 7, 8. So oxygen on the right is in contact with 8, and the oxygen on the left is in contact with 8 as well. That's what we need. The puzzle is now complete, and this is the formation for carbon dioxide. We can redraw it in a little bit nicer form. And you may see it drawn something like this. And we can put those lone pairs, they're called, around the oxygen. We can just spread them out. And that's a good picture of the Lewis diagram for carbon dioxide. If we leave off the single electrons, it could be drawn something like this. And that indicates carbon dioxide. Next, let's look at a water molecule. That's 2 hydrogens bonded to 1 oxygen. H2O is the formula. So oxygen's going to be our central atom for this. There's no way that hydrogen could be a central atom because it only has 1 electron that it can bond to other things with. Alright, so when it comes to hydrogen, hydrogen needs to be in contact with 2 electrons. So we should just form 1 bond there and 1 bond here. Now the hydrogen's happy because these hydrogens are in contact with 2 electrons, and the oxygen is happy as well because if you count up the electrons that oxygen is in contact with, it's 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is touching 8 electrons. Each hydrogen is touching 2 electrons. That makes everybody happy, and this is the right arrangement of the water molecule. So one thing we want to start to think about, though, for the future as well is what kind of shape do these molecules make? Like for carbon dioxide, I drew it as what would be called a linear molecule. It's a straight line. But water here, its molecule doesn't end up being straight. And we want to think about why that may be. So the reason comes from the repulsion that electrons have with each other. And see, when it comes to hydrogen being bonded to oxygen, there will be two lone pairs involved. Those 4 electrons are not bonded to anything. So they're going to actually repel each other. And not only that, but they repel the bonds between the hydrogen and the oxygen, making this bent shape because those bonds want to get away from the lone pairs. The reason why carbon dioxide is not bent and it's straight is because there's no lone pairs for carbon. Every electron that carbon had is bonded. And so these electrons here, they want to stay away from the other electrons on the other side of carbon. And to get as far away from each other as possible, they want to make a 180-degree angle between them. When it comes to water, though, we're not going to have 180 degrees between them. In a future video, I'm sure we'll discuss how to find out what the actual angle is between those bonds. You have to consider the 3-dimensional nature of the molecule, and we don't have to do that just yet, but it's just good to start to think about how lone pairs can repel bonds. All right, how about ethylene? C2H4. All right, so that's a bigger molecule. The thing about carbons is they often like to bond to each other. They're very versatile in having 4 valence electrons. I mean, for one thing, they need to bond to quite a bit in order to fulfill the octet rule. They need to be in contact with 8, so we can form many bonds, and one of the easiest ways for them to bond is just to bond to each other in what could be called chains, carbon chains. Let's see, we've also got 4 hydrogens. I'm going to spread those out a little bit here. Each hydrogen supplies 1 valence electron to the situation. And we know they have to be bonded at least once, so we could do that. So all the hydrogens are happy. They're all bonded with 2 electrons. But are the carbons happy? Let's see. 1, 2, 3, 4, 5, 6, 7. This carbon is only bonded to 7 electrons. And this carbon here is only bonded to 7 electrons as well. So this tells us something about the bond between the carbons. It must be that this single bond doesn't tell the whole story. There must be more to it. And so it must be that these electrons will be shared as well. Now, all of a sudden, the carbons are in contact with 8 electrons total, and the puzzle is complete. So if we draw them in a little bit nicer form, ethylene can often be drawn like this. A double bond between the carbons and just single bonds to the hydrogens. No lone pairs. Acetylene is C2H2. Each carbon supplies 4 valence electrons. we're going to have two hydrogens supplying one valence electron each. We'll definitely want to bond our hydrogens to the carbons so that they form an actual molecule. We'll have to bond the carbons to each other. And it looks like we're going to need more bonds here because carbon is only in contact with 1, 2, 3, 4, 5, 6 electrons so far. So we'll need a double bond. And that gives us 1, 2, 3, 4, 5, 6, 7 electrons that carbon's in contact with. So we're going to make one more bond, a triple bond this time. And so the diagram for acetylene will look like this. Triple bond between the carbons and a single bond between the carbons and the hydrogen. Let's try hydrogen cyanide, HCN. That's a hydrogen, a carbon, and a nitrogen bonded together in a chain. Now the carbon is the most likely candidate for being in the middle. Carbons often are. So let's see, carbon's going to have 4 valence electrons, hydrogen supplies 1, and nitrogen supplies 5. Alright, so we definitely want to make at least one bond between all our elements. The nitrogen here is not quite happy yet. It's in contact with 1, 2, 3, 4, 5, 6 electrons. So let's go ahead and make a double bond there. Now the nitrogen's in contact with 1, 2, 3, 4, 5, 6, 7 electrons, which is not enough. So we'll try to bond it one more time. And that ends up working out here. So we're going to have hydrogen with a single bond to carbon and then a triple bond with nitrogen. There is going to be a lone pair, which is expected to go opposite the other electrons. So that would be a good drawing there of it.